CIET NCERT presents Audiobook of Science for Class 7 entitled Science. This is the lesson 13, Motion and Time, from page 143 to page 159. Let's listen to the lesson 13, Motion and Time. Page 143. In class 6th, you learned about different types of motions. You learned that a motion could be along a straight line, it could be circular or periodic. Can you recall these three types of motions? Table 13.1 gives some common examples of motions. Identify the type of motion in each case. Table 13.1, some examples of different types of motion. There's a table given here. In this table, there are 2 columns and 7 rows. In the first column, we have example of motion. In the second column, you have to fill in the type of motion. It can be along a straight line or circular or periodic. Row 1. Soldiers in a march past. Row 2. Bullock cart moving on a straight road. Row 3. Hands of an athlete in a race. Row 4. Pedal of a bicycle in motion. Row 5. Motion of the earth around the sun. Row 6. Motion of a swing. Row 7. Motion of a pendulum. It is common experience that the motion of some objects is slow, while that of some others is fast. 13.1. Slow or fast? We know that some vehicles move faster than others. Even the same vehicle may move faster or slower at different times. Make a list of 10 objects moving along a straight path. Group the motion of these objects as slow and fast. How did you decide which object is moving slow and which one is moving fast? If vehicles are moving on a road in the same direction, we can easily tell which one of them is moving faster than the other. Let us observe the motion of vehicles moving on a road. Activity 13.1. Observe figure 13.1. It tells the position of some vehicles moving on a road in the same direction at some instant of time. Now, observe figure 13.2. It tells the position of the same vehicles after some time. From your observation of the two figures, answer the following questions. Which vehicle is moving the fastest of all? Which one of them is moving the slowest of all? The distance moved by objects in a given interval of time can help us to decide which one is faster or slower. For example, imagine that you have gone to see off your friend at the bus stand. Suppose you start pedaling your bicycle at the same time as the bus begins to move. Page 144. The distance covered by you after 5 minutes would be much smaller than that covered by the bus. Would you say that the bus is moving faster than the bicycle? Figure 13.1. Vehicles moving in the same direction on a road. Here we can observe a lot of cars. The first car is grey in color. Behind that is a car blue in color. Behind the blue car is a white car. The white car is almost parallel to a light blue car. Behind the white car is a green car. Behind that car is a van. Behind the van is a red-colored car. Behind the red-colored car is an olive-colored car. And at the end, we can observe another light blue-colored car. Figure 13.2, position of vehicles shown in figure 13.1 after some time. The first car here is blue. Behind the blue car, we can observe a green car. Behind the green car is a light blue car and another white car. Behind these cars is a white van. Behind the white van is a red car, and closely behind is an olive car. At the end is a light blue car. We often say that the faster vehicle has a higher speed. In a 100-meter race, it is easy to decide whose speed is the highest. One who takes shortest time to cover the distance of 100 meters has the highest speed. 13.2. Speed. You are probably familiar with the word speed. In the examples given above, a higher speed seems to indicate that a given distance has been covered in a shorter time, or a larger distance covered in a given time. The most convenient way to find out which of the two or more objects is moving faster is to compare the distance moved by them in a unit time. Thus, if we know the distance covered by two buses in 1 hour, we can tell which one is faster. We call the distance covered by an object in a unit time as the speed of the object. When we say that a car is moving with a speed of 50 kilometers per hour, it implies that it will cover a distance of 50 kilometers in 1 hour. However, a car seldom moves with a constant speed for 1 hour. In fact, it starts moving slowly and then picks up speed. So, when we say that the car has a speed of 50 kilometers per hour, we usually consider only the total distance covered by it in 1 hour. We do not bother whether the car has been moving with a constant speed or not during that hour. The speed calculated here is actually the average speed of the car. In this book, we shall use the term speed for average speed. So, for us, the speed is the total distance covered divided by the total time taken. Thus, speed is equal to total distance covered divided by total time taken. Page 145. In everyday life, we seldom find objects moving with a constant speed over long distances or for long durations of time. If the speed of an object moving along a straight line keeps changing, its motion is said to be non-uniform. On the other hand, an object moving along a straight line with a constant speed is said to be in uniform motion. In this case, the average speed is the same as the actual speed. We can determine the speed of a given object once we can measure the time taken by it to cover a certain distance. In class 6th, you learned how to measure distances. But how do we measure time? Let us find out. 13.3 Measurement of time. If you did not have a clock, how would you decide what time of the day it is? Have you ever wondered how our elders could tell the appropriate time of the day by just looking at shadows? How do we measure long interval of a month, a year? Our ancestors noticed that many events in nature repeat themselves after definite intervals of time. For example, they found that the sun rises every day in the morning. The time between one sunrise and the next was called a day. Similarly, a month was measured from one new moon to the next. A year was fixed as the time taken by the earth to complete one revolution of the sun. Often, we need to measure intervals of time which are much shorter than a day. Clocks or watches are perhaps the most common time measuring devices. Have you ever wondered how clocks and watches measure time? The working of clocks is rather complex, but all of them make use of some periodic motion. One of the most well-known periodic motions is that of a simple pendulum. Figure 13.3. Some common clocks. A. Wall clock. B. Table clock. C. Digital clock. Page 146. Figure 13.4a. A simple pendulum. Here, we can observe a simple pendulum which is still and not in motion. Figure 13.4b. Different positions of the bob of an oscillating simple pendulum. Here, we can observe the pendulum at position O, which is almost at a 90-degree angle, position A, which is in the left direction of O, and position B, which is in the right direction of O. A simple pendulum consists of a small metallic ball or a piece of stone suspended from a rigid stand by a thread. You can observe this in figure 13.4a. The metallic ball is called the bob of the pendulum. Figure 13.4a shows the pendulum at rest in its mean position. When the bob of the pendulum is released after taking it slightly to one side, it begins to move to and fro. You can observe this in figure 13.4b. The to and fro motion of a simple pendulum is an example of a periodic or an oscillatory motion. The pendulum is said to have completed one oscillation when its bob, starting from its mean position O, moves to A, to B, and back to O. The pendulum also completes one oscillation when its bob moves from one extreme position A to the other extreme position B and comes back to A. The time taken by the pendulum to complete one oscillation is called its time period. Activity 13.2. Set up a simple pendulum as you can observe in figure 13.4a with a thread or string of length nearly 1 meter. Switch off any fans nearby. Let the bob of the pendulum come to rest at its mean position. Mark the mean position of the bob on the floor below it or on the wall behind it. To measure the time period of the pendulum, we will need a stopwatch. However, if a stopwatch is not available, a table clock or a wristwatch can be used. To set the pendulum in motion, gently hold the bob and move it slightly to one side. Make sure that the string attached to the bob is taut while you displace it. Now, release the bob from its displaced position. Remember that the bob is not to be pushed when it is released. Note the time on the clock when the bob is at its mean position. Instead of the mean position, you may note the time when the bob is at one of its extreme positions. Measure the time the pendulum takes to complete 20 oscillations. Record your observations in table 13.2. Page 147. The first observation is given just as a sample. Your observations could be different from this. Repeat this activity a few times and record your observations. By dividing the time taken by 20 oscillations by 20, get the time taken for one oscillation, or the time period of the pendulum. Is the time period of your pendulum nearly the same in all cases? Note that a slight change in the initial displacement does not affect the time period of your pendulum. Nowadays, most clocks or watches have an electric circuit with one or more cells. These clocks are called quartz clocks. The time measured by quartz clocks is much more accurate than that by the clocks available earlier. Table 13.2 Time period of a simple pendulum. Length of the string is equal to 100 centimeter. There is a table given here. In this table, there are 3 columns and 3 rows. In the first column, we have serial number. In the second column, we have time taken for 20 oscillations in seconds. In the third column, we have time period in seconds. Row 1. Time taken for 20 oscillations is 42. Time period is 2.1. You have to fill in the other rows. Units of time and speed. The basic unit of time is a second. Its symbol is S. Larger units of time are minutes, the symbol of which is MIN, and hours, the symbol of which is H. You already know how these units are related to one another. What would be the basic unit of speed? Since the speed is distance upon time, the basic unit of speed is meter per second. Of course, it could also be expressed in other units, such as meter per minute or kilometer per hour. You must remember that the symbols of all units are written in singular. For example, we write 50 kilometer and not 50 kilometers, or 8 centimeter and not 8 centimeters. Bojo is wondering how many seconds there are in a day and how many hours in a year. Can you help him? There is an interesting story about the discovery that the time period of a given pendulum is constant. You might have heard the name of famous scientist Galileo Galilei, who lived from AD 1564 to 1642. It is said that once Galileo was sitting in a church, he noticed that a lamp suspended from the ceiling with a chain was moving slowly from one side to the other. He was surprised to find that his pulse beat the same number of times during the interval in which the lamp completed one oscillation. Galileo experimented with various pendulums to verify his observation. He found that a pendulum of a given length takes always the same time to complete one oscillation. This observation led to the development of pendulum clocks. Winding clocks and wristwatches were refinements of the pendulum clocks. Page 148. Different units of time are used depending on the need. For example, it is convenient to express your age in years rather than in days or hours. Similarly, it will not be wise to express in years the time taken by you to cover the distance between your home and your school. How small or large is a time interval of 1 second? The time taken in saying aloud 2001 is nearby 1 second. Verify it by counting aloud 2001 to 2010. The pulse of a normal healthy adult at rest beats about 72 times in a minute. That is about 12 times in 10 seconds. This rate may be slightly higher for children. There's a thought bubble given here. A picture of Paheli is next to it. Paheli wondered how time was measured when pendulum clocks were not available. Many time measuring devices were used in different parts of the world before the pendulum clocks became popular. Sundials, water clocks, and sand clocks are some examples of such devices. Different designs of these devices were developed in different parts of the world. That is about 12 times in 10 seconds. This rate may be slightly higher for children. There's a thought bubble given here. A picture of Paheli is next to it. Paheli wondered how time was measured when pendulum clocks were not available. Many time measuring devices were used in different parts of the world before the pendulum clocks became popular. Sundials, water clocks, and sand clocks are some examples of such devices. Different designs of these devices were developed in different parts of the world. You can observe this in figure 13.5. 13.4 Measuring speed. Having learned how to measure time and distance, you can calculate the speed of an object. Let us find the speed of a ball moving along the ground. Activity 13.3. Draw a straight line on the ground with chalk powder or lime and ask one of your friends to stand 1 to 2 meters away from it. Let your friend gently roll a ball along the ground in a direction perpendicular to the line. Note the time at the moment the ball crosses the line and also when it comes to rest. You can observe this in figure 13.6. How much time does the ball take to come to rest? The smallest time interval that can be measured with commonly available clocks and watches is 1 second. However, now special clocks are available that can measure time intervals smaller than a second. Some of these clocks can measure time intervals as small as 1 millionth or even 1 billionth of a second. You might have heard the terms like microsecond and nanosecond. 1 microsecond is 1 millionth of a second. A nanosecond is 1 billionth of a second. Clocks that measure such small time intervals are used for scientific research. The time measuring devices used in sports can measure time intervals that are 1/10th or 1/100th of a second. On the other hand, times of historical events are stated in terms of centuries or millenniums. The ages of stars and planets are often expressed in billions of years. Can you imagine the range of time intervals that we have to deal with? Page 149. A. Sundial at Jantar Mantar, Delhi. B. Sand clock. C. Water clock. On close observation, we can observe a hole in the container of the water clock. Figure 13.6. Measuring the speed of a ball. Here, we can observe a boy who has rolled a ball. The various positions of the ball while rolling can also be observed. They can be measured with regards to a straight line. Measure the distance between the point at which the ball crosses the line and the point where it comes to rest. You can use a scale or a measuring tape. Let different groups repeat the activity. Record the measurements in table 13.3. In each case, calculate the speed of the ball. You may now like to compare your speed of walking or cycling with that of your friends. You need to know the distance of the school from your home or from some other point. Each one of you can then measure the time taken to cover the distance and calculate your speed. It may be interesting to know who amongst you is the fastest. Speeds of some living organisms are given in table 13.4 in kilometer per hour. You can calculate the speeds in meter per second yourself. Page 150. Table 13.3. Distance moved and time taken by a moving ball. There's a table given here. In this table, there are 4 columns and 5 rows. In the first column, you have to fill in name of the group. In second column, you have to fill in distance moved by the ball in meters. In third column, you have to fill in time taken in seconds. In the fourth column, you have to fill in speed, which is equal to distance upon time taken, and the unit you have to put in here is meter per second. Rockets launching satellites into Earth's orbit often attain speeds up to 8 km per second. On the other hand, a tortoise can move only with a speed of about 8 cm per second. Can you calculate how fast is the rocket compared with the tortoise? Once you know the speed of an object, you can find the distance moved by it in a given time. All you have to do is to multiply the speed by time. Thus, distance covered is equal to speed multiplied by time. You can also find the time an object would take to cover a distance while moving with a given speed. Time taken is equal to distance divided by speed. There's a thought bubble given here. A picture of Bojo is next to it. Bojo wants to know whether there is any device that measures the speed. You might have seen a meter fitted on top of a scooter or a motorcycle. Similarly, meters can be seen on the dashboards of cars, buses, and other vehicles. In figure 13.7, you can observe the dashboard of a car. Note that one of the meters has kilometer per hour written at one corner. This is called a speedometer. It records the speed directly in kilometer per hour. There is also another meter that measures the distance moved by the vehicle. This meter is known as an odometer. Table 13.4. Fastest speed that some animals can attain. There is a table given here. In this table, there are 4 columns and 9 rows. In the first column, we have serial number. In second column, we have name of the object. In the third column, we have speed in kilometer per hour. In the fourth column, we have speed in meter per second. 1. The object is falcon. The speed is 320 km per hour. The speed in meter per second is 320 multiplied by 1000 divided by 60 multiplied by 60. From here on, speed is only given in kilometer per hour. You have to calculate speed in meter per second. Cheetah, 112 km per hour. Blue fish, 40 to 46 km per hour. Rabbit, 56 km per hour. Squirrel, 19 km per hour. Domestic mouse, 11 km per hour. Human, 40 km per hour. Giant tortoise, 0.7 km per hour. Snail, 0.05 km per hour. Page 151. Figure 13.7. The dashboard of a car. Here, you can observe the dashboard of a car. There is speedometer in it. The speedometer is giving a reading of 0 km per hour. This tells us that car is in a state of rest. While going for a school picnic, Paheli decided to note the reading on the odometer of the bus after every 30 minutes till the end of the journey. Later on, she recorded her readings in table 13.5. Can you tell how far was the picnic spot from the school? Can you calculate the speed of the bus? Observing the table, Bojo asked Paheli whether she can tell how far they would have travelled till 9:45 a.m. Paheli had no answer to this question. They went to their teacher. She told them that one way to solve this problem is to plot a distance time graph. Let us find out how such a graph is plotted. 13.5 Distance Time Graph. You might have seen that newspapers, magazines, etc. present information in various forms of graphs to make it interesting. The type of graph you can observe in figure 13.8 is known as a bar graph. Another type of graphical representation is a pie chart, which you can observe in figure 13.9. The graph in figure 13.10 is an example of a line graph. The distance time graph is a line graph. Let us learn to make such a graph. Table 13.5 Odometer reading at different times of the journey. There's a table given here. In this table, there are 3 columns and 5 rows. In the first column, we have time in AM. In the second column, we have odometer reading. In the third column, we have distance from the starting point. At 8 a.m., the odometer reading was 36540 kilometers. Distance from the starting point was 0 kilometer. At 8:30 a.m., the odometer reading was 36560 kilometer. Distance from starting point was 20 kilometer. At 9 a.m., the reading was 36580 kilometer. Distance from starting point was 40 kilometer. At 9:30 a.m., the reading was 36600 kilometer. Distance from starting point was 60 kilometer. At 10 a.m., the odometer reading was 36620 kilometer and distance from starting point was 80 kilometer. Figure 13.8, a bar graph showing runs scored by a team in each over. Here we have a bar graph. On the x-axis, we have overs. On the y-axis, we have runs. In the first over, the team scored 1 run. In the second over, they scored 5 runs. In the third over, they scored 3 runs. In the fourth over, they scored 10 runs. In the fifth over, they scored 2 runs. In the sixth over, they scored 6 runs. Page 152. Figure 13.9, a pie chart showing composition of air. Here, we can observe the biggest composition is that of nitrogen, after that oxygen, and after that other gases. Figure 13.10, a line graph showing change in weight of a man with age. Here we have a line graph. On the x-axis, we have age in year. On the y-axis, we have weight in kg. This line graph is upward sloping. As the age is increasing, the weight also seems to be increasing. Take a sheet of graph paper. Draw two lines perpendicular to each other, as you can observe in figure 13.11. Mark the horizontal line as XOX dash. It is known as the x-axis. Similarly, mark the vertical line YOY dash. It is called the y-axis. The point of intersection of XOX dash and YOY dash is known as the origin or O. The two quantities between which the graph is drawn are along these two axes. The positive values are on the x-axis along OX. Similarly, positive values on the y-axis are along OY. In this chapter, we shall consider only the positive values of quantities. Therefore, we shall use only the shaded part of the graph you can observe in figure 13.11. Figure 13.11, x-axis and y-axis on a graph paper. Here, we can observe that on a graph paper, the second quadrant has been shaded pink. Bojo and Paheli found out the distance traveled by a car and the time taken by it to cover that distance. Their data can be observed in Table 13.6. Table 13.6, the motion of a car. In this table, there are 3 columns and 6 rows. In the first column, we have serial number. In the second column, we have time in minutes. In the third column, we have distance in kilometers. 1. Time 0 minute, distance 0 kilometer. 2. Time 1 minute, distance 1 kilometer. 3. Time 2 minutes, distance 2 kilometer. 4. Time 3 minutes, distance 3 kilometer. 5. Time 4 minutes, distance 4 kilometer. 6. Time 5 minutes, distance 5 kilometer. You can make the graph by following the steps given here. 1. Draw two perpendicular lines to represent the two axes and mark them as OX and OY as in figure 13.11. 2. Decide the quantity to be drawn along the x-axis and that to be drawn along the y-axis. In this case, we represent the time along the x-axis and the distance along the y-axis. Page 153. 3. Choose a scale to represent the distance and another to represent the time on the graph. For the motion of the car, scales could be time 1 minute is equal to 1 centimeter, distance 1 kilometer is equal to 1 centimeter. 4. Mark values for the time and the distance on the respective axis according to the scale you have chosen. For the motion of the car, mark the time 1 minute, 2 minute, etc. on the x-axis from the origin O. Similarly, mark the distance 1 kilometer, 2 kilometer, etc. on the y-axis as you can observe in figure 13.12. 5. Now you have to mark the points on the graph paper to represent each set of values for distance and time. Observation recorded at serial number 1 in table 13.6 tells us that at time 0 minute, the distance moved is also 0. The point corresponding to this set of values on the graph will therefore be the origin itself. After 1 minute, the car has moved a distance of 1 kilometer. To mark this set of values, look for the point that represents 1 minute on the x-axis. Draw a line parallel to the y-axis at this point. Then draw a line parallel to the x-axis from the point corresponding to distance 1 kilometer on the y-axis. The points where these two lines intersect represents this set of values on the graph. You can observe this in figure 13.12. Similarly, mark on the graph paper the points corresponding to different set of values. 6. Figure 13.12 tells us the set of points on the graph corresponding to positions of the car at various time. 7. Join all the points on the graph as you can observe in figure 13.13. It is a straight line. This is the distance time graph for the motion of the car. 8. If the distance time graph is a straight line, it indicates that the object is moving with a constant speed. However, if the speed of the object keeps changing, the graph can be of any other shape. Figure 13.12. Making a graph. Here we have a graph which has x and y axis. The x-axis represents time in minutes. The y-axis represents distance in kilometers. The interval on both the axes is that of 1. We can observe an upward sloping line here. This line tells us that at distance 1 kilometer, time taken is 1 minute. At distance 2 kilometer, time taken is 2 minutes. So on and henceforth. Figure 13.13. Making a graph. This figure is exactly like the one we observed earlier. It further tells us that at distance 3 km, time taken is 3 minutes. At 4 km, time taken is 4 minutes. At 5 km, time taken is 5 minutes. Page 154. Figure 13.14. Distance time graph of the bus. In this figure, we have a graph with two axes. The x-axis represents time in AM. The y-axis represents distance in kilometer. The interval on y-axis is that of 10. The interval on x-axis is that of half an hour. There is an upward sloping line here. On the line, there is a point T. The point T tells us that at 8:15 am or point A, the bus covered a distance of 10 km, which is represented by point B. Generally, the choice of scales is not as simple as in the example given in figure 13.12 and 13.13. We may have to choose two different scales to represent the desired quantities on the x-axis and the y-axis. Let us try to understand this process with an example. Let us again consider the motion of the bus that took Paheli and her friends to the picnic. The distance covered and time taken by the bus are given in table 13.5. The total distance covered by the bus is 80 km. If we decide to choose a scale 1 km is equal to 1 centimeter, we shall have to draw an axis of length 80 centimeter. This is not possible on a sheet of paper. On the other hand, a scale of 10 km is equal to 1 centimeter would require an axis of length only 8 centimeter. This scale is quite convenient. However, the graph may cover only a small part of the graph paper. Some of the points to be kept in mind while choosing the most suitable scale for drawing a graph are: 1. The difference between the highest and the lowest values of each quantity. 2. The intermediate values of each quantity, so that with the scale chosen, it is convenient to mark the values on the graph. And 3. To utilize the maximum part of the paper on which the graph is to be drawn. Suppose that you are given a graph paper of size 25 cm into 25 cm. One of the scales which meets the above conditions and can accommodate the data of table 13.5 could be distance 5 km is equal to 1 cm and time 6 minutes is equal to 1 cm. Can you now draw the distance time graph for the motion of the bus? Is the graph drawn by you similar to that in figure 13.13? Distance time graphs provide a variety of information about the motion when compared to the data presented by a table. Page 155. For example, table 13.5 gives information about the distance moved by the bus only at some definite time intervals. On the other hand, from the distance time graph, we can find the distance moved by the bus at any instant of time. Suppose we want to know how much distance the bus had travelled at 8:15 am. We mark the point corresponding to the time 8:15 am on the x-axis. This you can observe in figure 13.14. Suppose this point is A. Next, we draw a line perpendicular to the x-axis or parallel to the y-axis at point A. We then mark the point T on the graph at which this perpendicular line intersects it. You can observe this in figure 13.14. Next, we draw a line through the point T parallel to the x-axis. This intersects the y-axis at the point B. The distance corresponding to the point B on the y-axis, or OB, gives us the distance in kilometer covered by the bus at 8:15 am. How much is this distance in kilometer? Can you help Paheli to find the distance moved by the bus at 9:45 am? Can you also find the speed of the bus from its distance time graph? Keywords: bar graph, graphs, non-uniform motion, oscillation, simple pendulum, speed, time period, uniform motion, unit of time. What you have learnt. 1. The distance moved by an object in a unit time is called its speed. 2. Speed of objects help us to decide which one is moving faster than the other. 3. The speed of an object is the distance travelled divided by the time taken to cover the distance. Its basic unit is meter per second. 4. Periodic events are used for the measurement of time. Periodic motion of a pendulum has been used to make clocks and watches. 5. Motion of objects can be presented in pictorial form by their distance time graphs. 6. The distance time graph for the motion of an object moving with a constant speed is a straight line.
Page 156.
Exercises. 1. Classify the following as motion along a straight line, circular, or oscillatory motion. 1. Motion of your hands while running. 2. Motion of a horse pulling a cart on a straight road. 3. Motion of a child in a merry-go-round. 4. Motion of a child on a seesaw. 5. Motion of the hammer of an electric bell. 6. Motion of a train on a straight bridge. 2. Which of the following are not correct? 1. The basic unit of time is second. 2. Every object moves with a constant speed. 3. Distances between two cities are measured in kilometers. 4. The time period of a given pendulum is constant. 5. The speed of a train is expressed in meter per hour. 3. A simple pendulum takes 32 seconds to complete 20 oscillations. What is the time period of the pendulum? 4. The distance between two stations is 240 km. A train takes 4 hours to cover this distance. Calculate the speed of the train. 5. The odometer of a car reads 57321 km when the clock shows the time 8:30 am. What is the distance moved by the car if at 8:50 am the odometer reading has changed to 57336 km? Calculate the speed of the car in kilometer per minute during this time. Express the speed in kilometer per hour also. 6. Salma takes 15 minutes from her house to reach her school on a bicycle. If the bicycle has a speed of 2 meters per second, calculate the distance between her house and the school. 7. Show the shape of the distance time graph for the motion in the following cases. 1. A car moving with a constant speed. 2. A car parked on a side road. 8. Which of the following relations is correct? 1. Speed is equal to distance multiplied by time. 2. Speed is equal to distance divided by time. 3. Speed is equal to time divided by distance. 4. Speed is equal to 1 divided by distance multiplied by time. Page 157. The basic unit of speed is 1 kilometer per minute, 2 meter per minute, 3 kilometer per hour, 4 meter per second. 10. A car moves with a speed of 40 km per hour for 15 minutes and then with a speed of 60 km per hour for the next 15 minutes. The total distance covered by the car is 1. 100 km, 2. 25 km, 3. 15 km, 4. 10 km. 11. Suppose the two photographs given in figure 13.1 and figure 13.2 had been taken at an interval of 10 seconds. If a distance of 100 meters is represented by 1 centimeter in these photographs, calculate the speed of the fastest car. 12. Figure 13.15 shows the distance time graph for the motion of two vehicles A and B. Which one of them is moving faster? Figure 13.15 Distance time graph for the motion of two cars. The x-axis represents time. The y-axis represents distance. There is an upward sloping line A. It is almost at an angle of 45 degrees. There's another upward sloping line B. It is almost at an angle of 30 degrees. 13. Which of the following distance time graph shows a truck moving with speed which is not constant? 1. Here we have a graph on which on x-axis is represented time and on y-axis is represented distance. There is an upward sloping line originating from the midpoint of y-axis. 2. The x-axis and y-axis are same here. There's a line originating from y-axis which is parallel to x-axis. 3. The x-axis and y-axis are again the same. There's a line originating from the origin and it is in the shape of an upward sloping curve. 4. The x-axis and y-axis are again the same in this graph. There is an upward sloping line here which is dividing the quadrant into two equal parts. Page 158, Extended Learning Activities and Projects. 1. You can make your own sundial and use it to mark the time of the day at your place. First of all, find the latitude of your city with the help of an atlas. Cut out a triangular piece of a cardboard such that its one angle is equal to the latitude of your place, and the angle opposite to it is a right angle. Fix this piece, called gnomon, vertically along a diameter of a circular board, as you can observe in figure 13.16. One way to fix the gnomon could be to make a groove along a diameter on the circular board. Next, select an open space which receives sunlight for most of the day. Mark a line on the ground along the north-south direction. Place the sundial in the sun as you can observe in figure 13.16. Mark the position of the tip of the shadow of the gnomon on the circular board as early in the day as possible, say 8 a.m. Mark the position of the tip of the shadow every hour throughout the day. Draw lines to connect each point marked by you with the center of the base of the gnomon as you can observe in figure 13.16. Extend the lines on the circular board up to its periphery. You can use the sundial to read the time of the day at your place. Remember that gnomon should always be placed in the north-south direction as you can observe in figure 13.16. Figure 13.16. A gnomon placed in the north-south direction. Page 159. 2. Collect information about time measuring devices that were used in the ancient times in different parts of the world. Prepare a brief write-up on each one of them. The write-up may include the name of the device, the place of its origin, the period when it was used, the unit in which the time was measured by it, and a drawing or a photograph of the device, if available. 3. Make a model of a sand clock which can measure time interval of 2 minutes. You can observe this in figure 13.17. Here we can observe the process of making a sand clock. It has been made with the help of 2 jars and 2 cups with holes in them. One of these jars, filled with sand, has been kept over the other. 4. You can perform an interesting activity when you visit a park to ride a swing. You will require a watch. Make the swing oscillate without anyone sitting on it. Find its time period in the same way as you did for the pendulum. Make sure that there are no jerks in the motion of the swing. Ask one of your friends to sit on the swing. Push it once and let it swing naturally. Again, measure its time period. Repeat the activity with different persons sitting on the swing. Compare the time period of the swing measured in different cases. What conclusions do you draw from this activity? Did you know the timekeeping services in India are provided by the National Physical Laboratory, New Delhi? The clock they use can measure time intervals with an accuracy of 1/1,000,000th of a second. The most accurate clock in the world has been developed by the National Institute of Standards and Technology in the USA. This clock will lose or gain 1 second after running 20 million years. The chapter 13 of total 18 chapters of the book ends here.